Energy Division of the PUC. Thank you all for coming. This is our independent peer review panel meeting, and we are reviewing PG&E's Central California Coast Seismic Imaging Project. Just by way of introduction, the restrooms are located off the courtyard. If you go into the lobby and turn to the left toward the cafeteria, there are a couple of restrooms, and also off the courtyard, if you go toward the auditorium or where we have the hearing rooms, and you go to the right, there are additional restrooms. With that, and maybe just briefly go around the room. So, to introduce, I think most of us know everyone, but for the benefit of people on the phone, so we know who's here. I'm Eric Green with Energy Division of the CPUC.
And I'm Bruce Gibson with the County San Luis Obispo.
Ken Perret, PG&E Geosciences Manager.
I'm Steve Thompson with LCI.
Danielle Mills with the Energy Commission.
Casey Weaver with the Energy Commission.
Mark Johnson with the Coastal Commission.
Chris Wills, California Geological Survey.
Bob Anderson, Seismic Safety Commission.
Ray Chen, California Geological Survey.
Gordon Seitz, California Geological Survey.
Stu Nishenko, PG&E Geosciences.
Dan O'Connell, Fibro Consultants.
Harold Peterson, Diablo Canyon Independent Safety Committee.
Thank you for joining us.
I'm Robert Budnitz with the Diablo Canyon Independent Safety Committee.
Rochelle Becker, Alliance for Nuclear Responsibility.
John Giesman, I'm an attorney for the Alliance for Nuclear Responsibility.
Douglas Hamilton, a consulting geologist.
I'm Sherry McKee with Legislative Assistant to Supervisor Gibson.
Don LaFrance from the CPUC's Energy Division.
David Weissman, Alliance for Nuclear Responsibility.
And if there's anyone on the phone that would like to identify themselves.
Ryan Alexander, United States Nuclear Regulatory Commission, Region 4 Office.
Thank you. Okay, with that, I guess I'll turn the meeting over to Chris, do you want to
Put me on the agenda as making opening remarks.
Okay.
So I'll take the opportunity. Thanks. I think this is going to be a key topic in seismic hazard analysis, and this is something we covered in IPRP report number 6 about the site conditions, site analysis at Diablo Canyon. And looking forward to hearing what PG&E and their consultants have done and learned about site conditions at the site and how they're using those in the analysis. This is one of the, as I said, one of the most important factors in seismic hazard analysis.
Go ahead, Stu. Okay, well, again, we have a fairly packed agenda this morning, so without any further ado, let me introduce Dan O'Connell, who is going to be discussing 3D tomographic imaging beneath Diablo Canyon and focusing on data acquisition, processing, and the initial interpretation of. And then later this morning, Norm Aberson will be here to talk about using this data then to evaluate site response, and then also talk about hazard sensitivity at the plant. So with that, Dr. O'Connell.
Okay, thanks, Stu. So I'm going to talk about not just the 3D tomography in and around the plant, but also a 3D foundation model that's being developed and it's gone through several revisions to use as a framework, or a series of models actually, for looking at 3D site response. And that'll be something Norm will talk about, but I'm going to talk about how we create models to consider for doing those site response analyses. So most people have seen all this, so I'm going to move through some of this pretty quickly. But we can back up later. We've tried to leave close to an hour for questions. So if this seems a little fast, we can go back and cover it again. So the area we're going to focus on for this presentation is in and around Diablo Canyon. We collected data over a large area over 2 years. We collected data over 2011 over the entire Irish Hills with up to 5,000 live nodes distributed out. The nodes are in red, and where it's blue, there were also nodes. And then we had fiber-sized source tracks going through. So we had a wide aperture of receivers out for a wide aperture of source points, and we used those along with gravity collected by USGS. So the gravity stations are shown in red on the left. Our Diablo Canyon's here. Generally followed, access over rugged dirt roads. And then we added in data in 2012 around the plant. So this area in here, the second year, we put in a much denser configuration of sources and receivers. The sources are still limited, and those are in red, and the receivers are in black. The sources are limited areas we could access. Sometimes we could go off-road, but generally it was on dirt roads or paved roads. This is a much tighter, higher resolution deployment of receivers and sources. And so we had up to 4,900 live channels per any of these shots and over 8,000 shot points. The focus, as is pretty clear from this, is within about 1 kilometer of Diablo Canyon. I was trying to really focus on a 1 kilometer radius of what the structure is around and underneath Diablo Canyon. So the tomographic data, we had different resolutions of tomographic data. We had a tomography done with velocity and density over the entire area, about 20 to 24 kilometers at 200 foot on a side, well, cells, actually 200 by 100. And then higher resolution, 50 foot by 50 foot horizontal, 10 foot, and then 5 foot cells as we got shallower in the area closer to Diablo Canyon, about 5 kilometer by 5 kilometer area. And now I will show some isovelocity, isodensity surfaces and so those are defined as the shallowest elevation in the 3D model at the geographic position of a particular isovelocity or isodensity value. And those illustrate some first order crustal structure that is relevant to discussing developing a 3D velocity model beneath and around the Diablo Canyon area. So we had, both some cable deployments in certain key areas where we could get in near the plant. So this is an example of the highest resolution tomography we had in this area. So these are in feet, so there's 20 feet there. This shows the shallow fill and weathering that is really prominent as you get closer and closer to the sea cliffs with lowest velocities. And then eventually you get into velocities that are associated with less weathered to almost unweathered rock underneath. And we could use some of these higher resolution deployments to check the tomography we did at larger scales. So the way we developed the velocity models was to initially invert travel times and gravity independently, build independent models, and then invert them together. And then at the final stage, refine the grid spacing and increase the resolution and make sure that the final velocity models had zero residual travel time biases as a function of offset. And that's just what's shown here is that this is offset in feet, so this is like the highest resolution, shallowest grid that goes to 300 feet below sea level. And this is the residual difference between the observed picked travel time and the synthetic calculated travel time using the final model. So these are the mean residuals, 2/3 of a millisecond. Our sample rate in our data was 2 milliseconds. So just to give an example of some coverage from some of the sort of higher resolution but still deeper inversions right at 7 feet above sea level. So I just guess this is on a timer, so I'm sorry, but I'll just flip back. So here in this area, the magenta is usually thousands to tens of thousands to almost 100,000 arrays in a cell. Generally, the lowest we have in here is in the the low mid tens, low velocity zones sometimes, which are shadow zones, which don't get a lot of rays. This shows on a scale of red, magenta to blue being slow and red magenta being fastest, that there's sort of already the outlines of a little higher velocity blob that leaks down toward the plant itself. And then here's an area of thick soil on a marine terrace, and with the fan complex, there's Diablo Creek, probably the paleo channel of Diablo Canyon up here, and there's an extensive fan complex of low velocity sediments. And so I'll just step down through this to sort of show the ray coverage in the area that we're going to focus on, which is within 300 meters below sea level and shallower beneath the plant and around the plant, to try to build a 3D velocity model that's representative of structure, of velocity structure in the plant for the purposes of calculating site response. So this one is, at a little less than 300 feet below sea level. We have, this is in the joint version model. We've saturated pretty much all the cells here with thousands of rays. And again, at almost 500 feet below sea level, we've saturated all the cells with rays. You can start seeing the hints even in the coarser velocity model of, some of the high velocity bodies that show up in and around the Diablo Canyon area. This is Cretaceous sandstone, and then eventually you're in Franciscan rocks here. There's actually the pillow basalts, for light out here. There's Franciscan melange and such up here, and this is actually near Los Osos in the basin. So as you get almost 700 feet below sea level, you finally get less than thousands of rays and the hundreds of rays under here, and that was just due to the coverage of the source and receivers. And then I'm going to show just an example of what these structures look like in cross sections. So, I'm going to show a series of cross sections in addition to this one shown in magenta here. So I'll start from the one shown in magenta. So this goes up through one of these, highest velocity bodies. And what I mean by high velocity is it's 6 kilometers per second. You don't typically see that embedded in shallow tertiary rocks in California. It's diabase. There's diabase outcrop. I can show you a picture of it. So they're thick sections that are similar, thin. The thin can be alteration. It can be diabase. The stuff that's 5 and 6 and above is probably just diabase, but they have magnetic anomalies associated with them. So there's mapped diabase all throughout the region. Here's the plant. There's on all sides of it, offshore, onshore, north, south, east. It's a pretty pervasive feature in the surface geology. It looks like outcrop of either diabase or basalt. I think that's pillowy. And then I'm going to show some cross sections to sort of show what the shape looks like in the subsurface of some of these things. So these start having what is a classic called saucer-shaped sill morphology. Some of them are kilometers wide. Some of them are, like half a kilometer wide. I'll show some more perspectives that make that more vivid. So this is a 3D perspective looking up through a tomographic model from beneath sea level. So here is the Diablo Cove, all right? An outline Diablo Cove looking up at it, and you're looking to the northeast. So this is a slice, what you're looking at here. Once you get red, you're at 4 kilometers per second. Now the typical velocities in this Obispo formation, the airfall tufts, and even the stiffer sandstone layers is usually somewhere to 2 to 3.5 kilometers per second. So when you hit 4 kilometers per second, you've either hit the dolomitized, altered stuff, or 5 to 6 kilometers per second in actual diabase. Yeah. So this is a classic in the north-south. This is looking, so I have an east-west section intersecting a north-south section here.
And I'm sorry, Dan, I don't quite I don't quite understand what we're looking at here. I mean, it is San Francisco. It looks like the inside of the Fillmore East or Fillmore West.
Depends how long you were in there. Right?
Yeah, right.
So if you look down, Diablo Cove is the plant is just sitting on the terrace.
Are we looking plan view?
But we're looking from underneath. We're looking from below sea level up at sea level. Okay. So we're about this is 300 meters below sea level. So we're
That
just a little
plane-
bit,
The plane on the bottom.
yeah, plane on the bottom is 300 meters below sea level. This plane up here is sea level, okay? And so the velocity, we superimpose the velocity of air here as the dark blue black, okay? And then the lowest velocity superficial stuff is the light blue, okay? So this shows some of the jetties and the two peninsulas that form Diablo Cove. This would be the northern peninsula. We sometimes call Slough 2. This would be near the intake, I think, is out near here. And correct me if I'm wrong. I think the intake for the power plant is right around in here. And we're looking from below up. And the reason I do this is so we can see the subsurface and I could still give you a geographic reference point to look at, that you're looking at Diablo Cove. So let me see if I've got it. So this is Diablo Cove, all right? There's the discharge plume. There's what we call Slough 2. The intake's down here. The plant's over here. So I'm going to flip that. So we're looking up from beneath as if we were, we removed the ground and we have two cross sections.
So there's a cross.
So is this a horizontal section?
It's three sections turned on at once. It's a horizontal section turned on up here.
At what depth for the velocities of the diabase and so on? What are we looking at there?
So this is 300 meters below sea level, and this is sea level right up.
So this is 3D all the way from 300 up.
Yeah, but it's just two horizontal, two vertical slices, an east-west slice here. Okay, and I'm going to move the slices.
So is there a match line? There should be a match line.
Can you indicate where the plant is?
Yeah. So I'm going to go back. So here's the plant. Okay. Here's Diablo Cove. All right.
Well, I see it on there.
See this peninsula here? That's called Slough 2. I'm going to point to Slough 2. I'm going to point to the intake over here. You see these little jetties here?
Yeah.
Yeah? Okay, we're going to go back down. So you see these jetties? Okay. Those on the south end of the plant. The intake's in here. Diablo Cove. See, this is the coastline. It's sort of, rough, but it's the coastline. All right. Okay. Diablo Cove. This is the Slough 2 northern peninsula. Okay. This is the southern peninsula of the intake.
Flipped around.
So that we're looking from underneath. Everybody's used to looking down. We're going to look up. Okay. And the reason to do that is so that we can see structure.
Are we looking at the inside of a box?
Yeah, you're looking at a side of a box. You're looking at a cutout. Yeah. Okay. So what I'm going to do, I toyed with just turning off this guy so you can just see, it's probably 1, 2, 3. Yeah. Let me flip through them. I'll show you. There's one where I turned off the east-west, and I just left the top, sea level, and a north-south line. So you're looking at that side of the
vertical cross section.
Yeah, these are all vertical cross sections juxtaposed with a horizontal one at sea level, so you can see where you are geographically.
Okay, so you have the top of the box and the sides of the box.
Yeah, and then I turn other sides on. Turn the other side on. Yeah. Okay. So this is easy. This is like there's the plant. Yeah, there's a little terrace.
Hey, I was starting to get that. So let's go back.
Okay. All right. Good. All right. So this is what we mean. This is a classic sort of saucer-shaped sill complex, and then there's embedded, shallower ones. Shorter dimensions. Some of them are flatter, some are more saucer shaped. This is, we didn't, obviously we didn't have sources offshore here. We happened to have receivers out here, so we had some ray coverage intermittently in here. And some are connected, and you actually have to go surfing around in 3D and see that actually a lot of these are connected. They connect and then they branch, and they connect and they branch. They often look like separate little bodies, but if you cut slices in cross-section, you can start mapping them out in 3 dimensions.
And so you're calling everything in red here the diabase? What's that velocity?
It's starting at 4 and it goes to 6. So it's either, in looking at the velocity logs you have out there, it can be, it can be a thin diabase with a zone of alteration around it. It doesn't itself, except as you get above 5, probably it's diabase itself. And so, these are distributed around in space. They're not generally right under, like, the turbine building or all of the turbine building. They're not under all of the containment structure. They sort of edge in and around. But they're at different depths, and this is really common in these complexes that are mapped, that you may have the juxtaposition vertically of up to like 6 different sills, depending on how.
Dan, you have the surface mapping, and there's a couple of velocity logs from way back, and geologic logs to a couple hundred feet down. Have you compared those?
Yeah, the deepest logs I've got, none of them hit the diabase itself. They hit a lot of them are in dolomite, so there are logs up northeast of the plant. They're in the dolomitized section.
And is the dolomite within that 4 kilometer per second?
Yeah, it can be. Yeah. In fact, it can be just as
So,
fast.
for example, the velocity logs that were done not too long ago at the ISFC are in high velocity material.
Right. Relative to your typical discipline velocity.
How does that map into your velocity model here?
I'll show you. But it's ISFC. These, like at IPRP, if they'd gone another 100 feet, they should have hit the really fast stuff. Okay, so just to go back to more conventional view, you look at this. This is moving. This is pretty much centered through the latitude of the facility. Okay, and then I go 50 feet. These are 50 feet across. This is 50 feet north of this, 50 feet north of this, and so that you can sort of see what the variation is over short distance, in particular areas. That these things do, change a little bit as you go along, and sort of in a high res stepping horizontally. But again, it shows classic sort of saucer shape, sometimes more tabular shape of some of these bodies, and how irregular they appear to be in any cross section. But as I said, if you actually look through, you start connecting a lot of these. But they occur at different elevations. Like this is an example. You've got like 3 different elevations, different bodies in there. So that when it came to selecting a depth, obviously there's some logistics constraints on how big a 3D model can be for doing site response. But also we were looking at, well, do we capture most of these irregularities? And it's going about 300 feet below sea level captures most of those really well. They show up really well.
Dan, I think I'm going to ask a question that's kind of outside the line of your discussion here, so I think that I direct it someplace else. So, in our last meeting, we spent a lot of time looking at the reflection seismic and talking about the tectonic models for the Irish Hills. And it looks to me like your details of the distribution of the diabase is more detailed, closer to the plant, and not really used in the development of those tectonic models. So was there a discussion of whether what you're seeing in terms of the distribution, the 3D distribution of the diabase, are you thinking of that as only the way that material was intruded, or are you looking for any tectonic disruption of that material? Is that something you look for?
Yeah, that's. I think I get your point.
There's lots of weird patterns of distribution of diabase.
Yeah.
Is that original patterns of how that stuff was intruded, or has it been rearranged by faulting?
I think the answer is maybe and maybe, right? I think probably for the original distribution, I
mean, what's striking to me is how continuous some of these saucers are. In other words, when you look at generally marine imaging of these things by industry, these are very simple. Have a lot of similarities, and those tended not to be disrupted by tectonic faulting afterward. All you saw really there was what they call the force fold disruption due to the intrusion itself, and they were mapping the whole complex as you can have both reverse and normal faulting associated with the volume of the intrusion. into sedimentary rocks. I mean, I have supplementary slides showing different examples of that. And, that was one of the things that really confounded us, around the plant, was then starting to see, just looking at the implications of the thickness variations of some of these, we realized then we're looking at, if we do have tectonic faulting, we're looking at a mix of force fold and tectonic faulting. If we're, it's not a clean, oh yeah, we can interpret all this in terms of tectonics. We have another very large significant signal that we have to consider when we look at the structure above these things, because they do disrupt, create, a prominent structure of their own.
Sorting out any later faulting that disrupted the diabase would be...
Well, the clearest thing would be on large-scale faulting, and you just offset saucer shapes.
Right.
That would be most like, that'd be easy. That'd be easy.
We never found opportunities to do that.
Yeah, and it just,
cases where that helped inform the large-scale tectonic model to use these as offset features.
Yeah,
that was part of the question.
That was part of the question, is did you look for those? We didn't hear any discussion of that in our last meeting, so I wanted to make sure that was
and something
part of the...
that is we're still looking at. It's sort of like, I said there are 100 theses in this data. There's a lot you can, of data mining you can do. I looked, it was low-hanging fruit. It was like, oh, it's an obvious thing, But it's like a lot of stuff out here. There's not a lot. It's not often easy or obvious to do things. There's complexity, and it requires a serious effort to figure that out. So,
I wondered whether is there a volume of reflection seismic data that goes along with this? I mean, this was collected as a high-resolution 3D volume.
If you go back to the acquisition maps, we realized the only way we're going to image down to so many hundred meters, given the limitations of the huge facilities and where we're going to access, was to do high resolution tomography in the shallow, and then at some depth we start to, and it's just like industry seismic use or optimized over depth range. So we have reflection seismic starting at 300 or 400 meters down, and that becomes the imaging tool in that depth range. And then we hit basically something that looks like basement in terms of its acoustically quiet at 600, 700 meters. So we have about 300 to 400 meters to 600 to 700 meters, and then you're basically into fairly acoustic quiet stuff. So we do have that data.
A couple things there. One of them is, at some point, go back. I've got some questions about the ray azimuth and density distribution, minimum offsets, and things like that are discussed in the report. But it seemed to me that the first time you showed us what you thought was a diabase intrusion, a very high velocity tomography result, it was overlaid with a seismic reflection section, and I'm thinking it was from this data set.
Yeah.
My concern was that the velocity anomaly in the tomography did not line up with the reflections. You should see a huge reflection off of that much velocity contrast. And
I showed you one where it was too shallow reflection to really get. We didn't have the near offset. So we were trying to migrate basically, almost the refractors. It's not a good scenario. So that's why I'm saying, if you use a more cautious approach to how you look at the reflection data, you'd start at, given.
So you don't have any reflection data control here.
Yeah, we don't have the consistent control in the first 200 to 300 meters.
And so the only control you have are the borings.
Yeah, we have velocity control for borings, and we have millions of rays. Okay, you have velocity.
Well, but what I'm getting at is that it's its own data set. That does not have an independent control. The tomography, you go through a long discussion about the limitations of the tomography, and I think that's important in coming up with the questions about the uncertainties of the velocity determinations. But can save that for a little later.
Okay, so and the purpose of showing these is to show the structure around Diablo Canyon in a larger context. So this velocity, so this is an isovelocity surface, so this is elevation, okay? For instance, out here you're at 5,000 feet or more below sea level before you you hit this velocity that we typically associated on the south coast here with being, well into the Franciscan basement. So Franciscan basement's relatively shallow here. It's below a veneer of Cretaceous sandstone. And then, we cross, and it's mapped, there's exposure, double rock here, Franciscan basement, there's a Franciscan basement exposed to the surface. Then there's inferred, beginning the basin. We'd expect, most of the basin is relatively filled with lower velocity material, that this area here is the area that the magnetics also delineates, and
Just for perspective, Dan, back on that image, that's the Pismo Syncline, and then the northern Irish Hills, and the Los Osos Valley, and all the way to the north side of Los Osos Valley. Is that what we're looking at here, the area?
No, this is
Okay.
Los Osos Valley Road.
Los Osos Valley
is right around in here. So this is, the prominent north-facing hill front you see from Los Osos Valley Road.
The area of outcrop of Francisco.
Yeah, of outcrop of Francisco. You see large, serpentinite bodies exposed.
So those planes you have going through are all strands of the...
So these are from the onset, mapping of the Los Osos Fault. This would be what they call the Edna B Fault. Yeah. And it was just illustrating, it's not all the planes by any stretch, but it's trying to illustrate where some of the planes.
I'm just trying to get myself oriented to your image here.
Yeah. So we're looking, east, southeast from above. And, this is the south, this is Point San Luis,
Okay.
And the harbor
That
back
is just
here.
the shoreline there.
Yeah, and we're,
Roughly.
because the acquisition was, close to shore onshore, that was sort of limited where we had coverage. But what I want to show here is that even though we've crossed over into what's mapped at the surface here as tertiary basin rocks, unlike everywhere else except these altered rocks that appear in the Tidewater well that are also higher velocity, we have this area of altered dolomitic rock and diabase that continues to maintain a velocity shallower than you typically see in the tertiary units. And if you go to a really high isovelocity, so that even you start to see, places where this Franciscan doesn't even reach this velocity, this area is really anomalous because of probably the mixing of the diabase and alteration. So it isn't just at the plant, it isn't those sills I just showed you at the plant. It goes both southeast of the plant and extends along the coast up to basically, cut to the chase, probably the source of the diabase is probably up there. Because if you go below here at 2.5 kilometers, you hit 6.4 kilometers per second. You don't hit a velocity like that, like in Dean Hardbeck's model, much deeper anywhere. And you hit a density of about 2.8 grams per cc. So that's probably where the diabase came up. And it helps, I think, discussing with Jeff Runrow, it makes sense a little offshore vent here in terms of the airfall ash distribution. It's not right at the source of the plant. The source is somewhat distal to the plant. So anyway, explains, basically a distribution of diabase for about 7 by 4 kilometers, roughly, area there. And again, if you look at it in terms of density, this area again is dense, shallower than typical in the basin, except for the other areas of dolomitic alteration. And again, it continues along the coast here, fairly high density. Okay, so I raced through all that to get to the 3D foundation velocity model. So we have, as we alluded to earlier, we have some velocity constraints from 3 deep boreholes that are in sort of the footprint area that we're interested in. These are downhole data. So I have travel time picks from those. So I'm going to focus on the shear wave travel time picks for those because I'm going to focus on the shear wave model. I have 6 center points of either distributed 2D distribution of stations that I did surface wave dispersion or a cable and a high, density cable estimates of surface wave dispersion. And then we have a region that, for the purposes of trying to develop a subset of models that we're going to run through very time-consuming, I think, full 3D site response calculations, trying to use identify an area where we look at the mean characteristics of any of the proposed 3D models and evaluate is their amplification generally low, mid-range, high, and try to pull out basically 3 models to represent those sort of classes for the purposes of doing the more extensive 3D site response calculations. So we do have data constraints, and so I'm going to use those data constraints. So you've seen PR16, that was a 3D model, a little bit smaller area. This is a bigger area. We've extended it north to get more of the Diablo Canyon.
So it's PR16 you're talking about is the model presented in the report from September.
Yeah.
So you thought this is what this is
that's
going beyond that model.
Yeah, that's a starting point. And then, Norm's assembled, a peer review panel just for looking at site response questions. And they looked at that and they developed a set of questions and comments. And so we're developing these models anyway, so we wanted to incorporate, all the comments they had and see if we could address those as we extended the model to incorporate more of, one of the comments was more of the topography east of the plant. Maybe it wasn't so important to have as much out here, some of the topography north of the plant, so the model expanded laterally. And then, as I showed you earlier, you go down to about 300 meters below sea level, and you've captured most of those diabase bodies and associated alteration, all those saucer-shaped structures. Generally, are captured within 300 meters below sea level. So going down there gives you an opportunity to get as it turns out, a relatively constant velocity as an input boundary condition at the bottom, which would be a desirable thing if you do it. So it accomplishes that going that deep. It captures the complexity up to the surface. And so what I want to do is I generated a lot of correlated random models, and like 500,000, and then I grade them against all the data constraints I have from those 9 observation sites spread across the site. And then I found, up to the time it was running, I actually found 400, but 346 that matched the data at those 9 sites within the picking uncertainties, the travel time picking or the dispersion picking. And then I looked at the mean of, there were 256 50-foot cell 1D SH amplifications, and looked for individual models. They fit all the data that were low, mid-range, and high to see if we could come up with this on the order of 3 models that might actually genuinely.
Before you go on, I have a question here on your third bullet.
Yeah.
Why is size C listed twice? It says size, that's.
Oh, it's supposed to be NC, which, it should be NC in south. Okay. That would probably have to do with sleep deprivation. Okay, so there's a northern cable, a central cable, and a south cable. And the reason it was split up that way was so that we didn't estimate dispersion over the outlet box structure, which wasn't that informative. And then, so if we're going to pick 3 models from 346 that all fit the data. Well, and then I'm going to show you what I mean by fit the data. So, these are the 3 boreholes where we have downhole data to a couple hundred feet, 70 or 80 meters. And so the diamonds are the observed picks. I took the earliest ones because there were, particularly on this line, he had trouble picking. So fortunately, he picked everything. I just took his earliest picks. And I had to adjust the later picks because his picks had shifted to a different cycle. But the key thing to get the shallow right is to intersect these ones at shallow depth. Now, every model, including the perturbed randomized models, they all hit within the picking uncertainty. So this is the average misfit is less than 2 milliseconds. That's consistent. That's easily within the picking uncertainty for this data. And then, we had the surface wave dispersion, along the coast. So we have, this would be the size north, central, and south. North, so the center of the cable here, central, center of the cable here, and south here. These are the closest, this is closest to the sea cliffs. This is starting up Diablo Creek, moving a little bit away from the sea cliffs, and this is also set back a little bit more from the sea cliffs. So the slowest high frequency dispersion observed is closest to the sea cliffs. So this just lists, the minimum sort of phase velocity that shows up at each of these sites. And then inland, we have a point centered amongst this cluster, another point centered in this cluster, and a point centered amongst this cluster. They tend to have higher minimum phase velocities. It's actually not a surprise why that is, because if you look at the original topography, pre-construction topography, and compare it to the area after excavation construction, we actually removed up to over 17 meters of material up through some of this area where you don't see some of the slower phase velocity, so you just removed it. So what I did was, my first modification I made to the PR16 model was to refine it based on this a little bit more. It's like, okay, it really does have a phase velocity, typically 500 meters per second or higher in here. So I said, okay, I modified the model so at least it did. And then I did an initial randomization searching for models that fit all the data, just to create a new baseline model. So I took the geometric average of 8 models, randomized models that fit the 9 stations, and then use that as the new baseline model.
And why, I'm afraid I'm going to have to get backed up at some point to understand what we walked through here, what we've been looking at. But in terms of choosing 8 models to average, where did those 8 models come from? And when you say fit the data, what data exactly are you fitting?
This data.
Which is what? What are we looking at here?
This is shear wave travel time as a function of depth for downhole
straight
measurements.
down those holes.
Well, they're usually, the source is offset about 15 feet, so they don't create humongous tube waves.
Okay.
So this was a 1978 report. So that's one constraint.
And what are the clusters of points along each one of those? Lower observed baseline, lower mid-range, upper, what?
So this is what the smooth baseline model created. This is what a model produces systematically lower amplification. This is sort of mid-range amplification. And this model produces systematically high amplification. They all produce fits to the data within the picking. Okay.
Within 2 milliseconds over 80. What's the velocity uncertainty there? Because we're really looking at the derivative of that curve to know what the velocity is, at least in the interval, right? Because you're just doing travel times down to depths. What we're interested in is velocity.
I'll show you the models. I put those with the dispersion. So these are the other constraints. You've got to match. These are picking uncertainties on the dispersion. These are the fit for this one. So this is a baseline model. The reason why I averaged 8, and 8 had to fit all 9 data points within the picking uncertainty. The reason I did a geometric average of those is those 9 points only constrain a certain depth range. And then the rest of the randomization of those models is just random. So by doing a geometric average, I recovered pretty much a model that didn't change below the depth of the constraint that much, because I wanted to overall only have to change the model the minimum amount necessary to be consistent with all 9 data points. You could try to write the gradient terms for shade derivatives to do this as a linearized inversion. And the time I have, and frankly, as a more comprehensive test, just generating hundreds of thousands of models gives me more assurance than any linearized inversion. So that's what I did. Anyway, So this is, the next dispersion point. All the models fit well within the uncertainty, but the models themselves can vary quite a bit. You'll notice they can't vary as much in the shallow. And this right here vividly illustrates that the constraints from those boreholes and the dispersion are, in the first 50 to 80 meters, not surprisingly, and then much more variability is allowed because it doesn't impact the fit to the data, the borehole, the downhole constraints, or the dispersion. So you walk through, again, not as much variability here, more variability allowed down in here. And as you get out to the coast, you get lower phase velocities, and most of that just the shallow part, there's more shallow, lower velocity material. Okay, so I took 346 models that all fit those 9 data constraints, and they also fit in the P wave, the tomography from 6.5 million first arrivals with typically hundreds to thousands of ray hits. And each one of these thin little curves is one mean of the 256 50-foot cell positions inside this red circle. So it just shows a range of models that all fit the data we have, how much variability you can get in amplification. And then the magenta is just the mean of all of these. So I said, okay, I actually need individual model realizations. These are all fit the data. And this is just, the blue is the model that consistently stays the lowest over the 1 to 30 hertz range. The red is the one that stays consistently the highest. And the green is the one that varies the least around pretty much getting close to the mean, so it's sort of mid-range. So I have a baseline model that is obviously not geologically realistic, because if you look at any sonic logs or anything, it's too smooth. Okay. So I have a randomized mid-range model. It's probably more realistic for calculating kappa and site response and things. And then I have a high and low. And at this point, we have something that we can look at and evaluate with more sophisticated 3D site response calculations. And this model's generated over the area I showed earlier. So we have a shallow intrusive complex. It's fairly broad actually, but for our purposes, if we extend a model down to about 300 meters below sea level, we capture most of the velocity variations associated with those intrusives. We generate a lot models that consist of all the data constraints we have, and then from those, we looked at trying to identify and evaluate, say, 3 models moving forward to characterize sort of low, mid-range, and high amplification in the plant footprint area.
And are those 3 models, if you back up one slide, are those 3 models shown there? The high, low? Because what I take away from that, actually, if you go back either to that, the fuzzy diagram, or the one just before that one, or the next one, what I take out of that, just in a brief look at it, is that at 10 hertz, there's considerable uncertainty as to what the amplification at the site's going to be.
Yeah, so you'd like to exercise that.
I put this on a linear scale, so I'll show similar results, but on a log scale. Okay, so keep that in mind. Okay, so but when he's going at 10 hertz, he's going from, let's say, 1.35 to 1.7 or 1.7
or 2 or whatever. Yeah.
Or 2. Okay, so you've got about a factor of 1.4, 1.5. Okay, so and in log cycles, that's going to be about a 0.45. Just so you want to. When we showed in natural log units, 0.45 is equal to that same range.
But still, in the lower frequency, well, in fact, in everything, all frequencies above about 2 hertz, it looks like there's considerable uncertainty in the amplification.
That's his job.
So, just slide it over and load up.
So while they're doing that, most projects will run alternative 1D profiles. So they'll just say I'm going to assume everything's flat layers, and they'll assume different possible flat layered models. What you're seeing here is the flat layered model doesn't apply to this region. So instead of saying I'm going to choose a suite of flat layered models, we're choosing a suite of 3D models, because we don't want just one. We want to capture what the range of amplification could be for different models. So that's what's very different from having this kind of data that we have versus what's happening at any other nuclear plant. No one else has data like this, so they're doing much simpler evaluations of the site response. And here we're able to take advantage of this. All right.
Do you want me to pass out this?
Yes.
Well, you get loaded up here.
Can you operate
Yes.
this for me?
Yeah.
It's been a folder I Yeah, that's what it says. So I thought I copied the whole folder over. Yep. Okay, so good morning. I'll talk about, so two things for you today. First, what was shown in the site response in the report that you had reviewed, and then I'll describe what we're doing moving forward, following up with what Dan had shown, and then also talk about the hazard sensitivity at the end. So the next one, please. So, this is not a room of ground motion people, so let me give you I'm going to start really basic with what we're doing in ground motion. So the typical way ground motion models are developed around the world is to, we need to have enough data from big earthquakes at close distances to build a model. And we don't have enough data usually at any one place, so we're going to go collect data from around the world from earthquakes that are in analogous tectonic regions. So we're going to start to group data together. And in the ground motion world, we group them by shallow, active tectonic regions, California and so forth, stable continental regions like the eastern United States, so things that have been sitting there for billions of years, and then subduction zones. So those things are separated. And then within those, we lump them together and start to build a model. Okay? When we do that, we describe site response, all of the amplification, by some simple parameters, usually the shear wave velocity in the top 30 meters. So it's just one parameter that we use. We describe how the waves propagate through the crust, complicated crust, just using the distance away. Okay? And we're going to describe the strength of the shaking just by the magnitude, and sometimes we describe also the depth to identify that's effects. So the penalty for this simplification is variability. We can't fit all of the observations. Okay, so site response, what you just saw from Dan, is much more complicated than just what is the BS30. Wave propagation through that 3D structure, all the way from the fault to here, is much more complicated than just distance away. And earthquakes are much more complicated in how they release energy than just magnitude. Okay, so next one. So I have to put an equation, and actually I'm going to have you look at 3, but these are really simple, okay? There's a lot of parameters, but we predict the ground motion at a given magnitude, location, so this is how far away you are, and a site condition, and we'll use these models. So GMPE is ground motion prediction equation. This is a model built by looking at data from all around the world and lumping it together. So this is a model saying for an average site, from an average magnitude, let's say 6 earthquake at 10 kilometers, what's the average ground motion? Okay, so if my site was average and my earthquakes were average and my wave propagation was average, then this would work. I'm going to misfit though. This is because of this very simple model. I'm not going to fit the data, and this is my misfit between my prediction and the observation, which we call a residual. The standard deviation of that is really important to us, and we call this aleatory. We treat it as that means it's random. We assume we can't predict what it is. So given a model where all I can say is I'm going to use these simple parameters for describing the earthquake process, my penalty is I'm going to have a big random term. And this is a large variability. Okay? So we assume, though, that this applies to all of the earthquakes and to all of the sites. Okay, the next one. So this is what we call the ergodic model. And if you read in the report, we talk about a non-ergodic model. So when we say ergodic, we're saying I'm going to trade space for time. I don't have a lot of recordings over millions of years at my site, but I can go look at recordings around the world, and I can then assume that their properties are all the same as at my site. Now we know that's actually not going to be correct. My site is going to be different, the wave propagation will be different, and so forth. So really, I have my average model around the world that I've developed. Okay, so these are what when you hear about the peer NGA, GMPEs and so forth, that's what they're doing. They're taking worldwide data and building this model here. But I know my site is actually going to have different amplification. You saw those peaks, for example, in some of Dan's plots. So instead of saying, what does the VS30 tell me, I'll say my site actually gives me higher ground motions, let's say at 5 hertz, and maybe lower ground motions at 10 hertz than an average model, average site around the world.
Based on, how do you know that?
Because my site's going to be different. So we'll get to some data to show you how we know what that could be, but conceptually, that has to be it. There is a correct site response. I just don't capture it completely with this simple parameterization. In addition, as the waves propagate through the earth, if I had a lot of earthquakes in one area, recorded at my site repeatedly, I could start to see what is the systematic difference from just knowing distance to actually knowing the wave propagation effects. And so we call that a path term. And then finally, the source might be different. Earthquakes in one area may be, magnitude 6s may be systematically more energetic than an average, or maybe they're less energetic. We talk about that in terms of stress drop, usually, if you've heard that term. So magnitude gives us total energy to release. A stress drop's going to tell me how that energy is released on the fault, how compact that energy is in space and time. If I compact it really small, I'm going to get and release it quickly, I'm going to get big ground motions. If I release it over a larger area or very slowly, I'm going to get low ground motions. So we know all those things should be there. If I do that, I'm going to get a much better fit to my data. So I'll have a lower misfit, okay? And this is now treated as our aleatory variability. The problem is, I may not know what these parameters are. In most sites, I don't know what they are. So we talk about our inability to know that. How big is the standard deviation of each of these? Is our epistemic uncertainty that I know what is going on, okay? But the framework here has to be, is the correct way to describe the problem. We typically just say, I don't know these, so I'm going to just assume they're all 0 and map their effect into a big standard deviation. That's what the ergodic model is. Okay, so the non-ergodic one, the next one, I'll show you, we can say, how do we know what these things are? So we now have data sets, I didn't show you some other introductory slides, but data sets where we have lots of recordings at sites. So I have, a site may have recorded 50 earthquakes in different directions and so forth, so I can see what is the repeated site response. It's recorded many earthquakes in the same direction, so I can see what is the path effect. And I can also see the source effects. What this plot or table shows you is the standard deviation in an ergodic model for different spectral periods. So this is the short periods and the long periods here. But the numbers are around 0.7 natural log units. So 0.7 is a factor of 2. One standard deviation is twice as high. One standard deviation down is a factor of 2 lower. Okay? If I say how much did that term that we call the amplification term, the site-specific difference from what VS30 would tell me compared to what my site really is doing, its standard deviation here is around 0.3. Okay, so we now have data to start to tell us how big our problem is or how far off we are when we start to use the ergodic model. Okay? The path term is shown here. Its number is around 0.4. Okay, and for the seismologists, when I talked about this, we actually see, this is telling me how much of the path term that I currently treat as random and unknown is actually knowable. Okay, I can know, if I had enough data, I can get at this and I can determine what that is. And it's actually, the knowable part here is bigger at high frequency or the short periods than it is at the long periods. Seismology tends to work in this long period range and treat this as random, but this is showing us from data, these things are not random, they're systematic and knowable. Okay, we can get at them. The last term is the source. How much could my average stress drop in one area deviate from the average stress drop in another in terms of its impacts on the ground motion? So when we compare earthquakes between California and the eastern United States, we might have earthquakes that are 50 bars in California, where there are an average of 150 bars in the eastern United States. Meaning when they have an earthquake of the same magnitude, same total energy release, they get a bigger ground motion than what we get. Okay, so this tells us how much that can vary. If you take all of these out, so if you really had the data, we know these things are there. There are systematic source effects, path effects, and site effects, but in most cases we don't have the data to get at them. Okay, but that doesn't mean they're random. It means we just don't have the data yet to tell us what it is. Okay, so those are two different things. All right, so these are things, these are our known unknowns. All right, these are stuff that we know should be there, but we don't have the data yet to control them. Our partially non-ergodic model that we've used at Diablo Canyon does some of this. Okay, it's going to deal with only trying to bring in the site term, and going forward, what I'll talk to you about at the end is how you can start to deal with these other pieces. If you're going to do this, we have to isolate the site term from the source and path terms. Okay, so that means I have to have enough data recorded at other sites from that earthquake to take away the average effect of was the source strong or weak, and is the scaling with distance different than average. Okay, and then we have to also deal with what is our uncertainty in this term. Okay, we don't get to use those smaller variabilities without the penalty of saying I'm going to have uncertainty in my epistemic uncertainty in my ability to estimate that amplification term. And that gets back to, we're going to deal with 2 earthquakes, and how big is the uncertainty with just 2 recordings, and we'll show you how I've dealt with that. The next one. So, in our last equations, okay, these should be familiar to you now. We're just having our global NGA models, and we're only going to deal with one of these terms. That's all that we've dealt with. So we're going to try to pull this term out, get an estimate of this, and its uncertainty, and we're going to use the rest of this variability here. So it's in between the fully ergodic and the fully non-ergodic model. We call this a single station sigma. Okay, the standard deviation when you take out the site-specific amplification effects out of the aleatory term. Okay. Right, so this is going to be the aleatory part there. This is going to be what we don't, an uncertainty in our ability to estimate that term. Okay. Next one. So when we do our standard deviations, how do we do this? This is kind of when we get to a deterministic approach. We put together something here that gives us a smooth transition from when you have no information to when you start to have data in terms of how we deal with it. So on a deterministic ground motion, we compute the 84th percentile ground motion. We take the median from our ground motion prediction equations, then we combine it with the aleatory standard deviation. What we've done here is this is the aleatory part, and just to be consistent, we've folded into this our uncertainty in the site term as well. As I get more and more data, this goes to this becomes big, this term drops out, then I have just the single standard value. If we have no data, then I'm going to get this thing. When n is equal to 0, we actually plug in 1, just so you don't worry about that. But this becomes the total aleatory or ergodic standard deviation again. So we have a smooth way of starting to bring this in. For Diablo Canyon, we're going to work with this with 2 here. So this is still a significant piece with a number of around 0.4, the same type of standard deviation you just saw from what Dan was showing. Okay, next one. This is this is the same thing though. We're going to from Dan, he developed the 3D velocity models. We can jump ahead. The power plant in this 3D sphere, the power block is right over this part in here. This is to the north, and this is to the south. We have recordings that are towards this end, and recordings that are towards that end that are on the softer material. The next one. So if we looked at the velocities that we had talked about previously, so you looked at the 4 boreholes that we had, those are shown by the black lines. Okay, and one of the comments in your report 6 was, look at this huge range. You know, you've got stuff as low as 700, and up here, why are we using 1200? Because that's what we were using for the power block. Okay, so if you look at this, where the power block is shown by the red. So this is using Dan's 3D model. The turbine building is further towards the coast. It's getting towards a softer material, and it has a lower velocity here. And these 2 sites here, ESTA 27 is to the south. That's one of our free field sites. And ESTA 28 is to the north of the plant. That's our other free field site. So you can see that this range that we're seeing from the boreholes, we're actually seeing as well when we're just looking at our velocity profile. So there is a huge variation. The point of this, though, none of these things are really 1D site response calculations. It's much more complicated than that. And just taking this profile and running the 1D is not going to capture the same amplification as what a 3D model is going to do. So instead of running a traditional analysis of 1D site response, where they would shift this up and down or have randomness about this, in the same kind of way that Dan was developing randomness into 3D models, that's the standard approach in the nuclear business. Take your profile, add uncertainty to it, run a bunch of 1D analyses. We're going to do multiple 3D analyses to capture the effects, okay? Where the 3D analyses are at least constrained to be consistent with the observations that he's got. And he's chosen those ranges of not to have the high and low velocities, but to have the high and low amplifications, because that's what we care about on the site response. What is the amplification that's coming through the whole thing? Okay, the next one. This is when we take the data, just to show you what we're doing. This is data from San Simeon and data from Parkfield. The blue circles are all recordings from those earthquakes that were in the peer database that was used. The red symbols are where the Diablo Canyon is. This is residual here, so that's the misfit. Remember, we had our model, and we had that term that was the misfit. This is the misfit here between what the model prediction is and the observation. And then I can look over here and say, let me look at other data sort of in this range. My average residual here is about 0.2 or negative 0.2. From that, I'm trying to take out the average source and average wave propagation effects so that I'm not mapping that into the site effect. For Parkfield, we're further away. So while these data are fitting the average model, you can see these at longer distances. There's a slope here. This meant that the distance scaling in the ground motion models is not fitting the observation. These data are falling off faster than what the model should be, so I don't compare it to 0. I compare it to data from a similar distance range so that I know I'm getting the same kind of effects. So what you see here in both cases, we're getting a similar residual, or at least a residual in the same direction. The next one?
Norm?
Yeah.
Before you go on, we've looked at this before, and the recordings at the plant are systematically low when you compare it to the other recordings of the same earthquake at similar distances. Have you looked back to see if there's any kind of pattern from those earthquakes, those other recordings at similar distances where you have a particular azimuth that has low amplification or high amplification?
Right. And
Or
so,
is this random?
we don't see systematic behavior, but to really get at that, I would like to have a whole bunch of stations in my azimuth, right? And so
Well-
these are sparse, or at least in different azimuths, so that I can really to refine the thing.
You'd like to have a bunch of the same azimuth.
Right, but the answer is if I put these on a map and contour them, I don't suddenly see, oh, this direction is really high and this direction is really low.
It's not an obvious pattern that jumps.
Correct, correct. But that's really what we're going to get to on all of this in the end, to improve our ability to map out side effect. It's going to require denser or additional instrumentation to get at this. Okay, next one. So if we repeat this process for a lot of different frequencies, these are those plots for the blue being San Simeon and the red being Parkfield, what it is at each spectral period, compared to 0, which would be the ergodic model, okay, to say everything is the same. So here, we're as a worldwide average. Here we're seeing at the higher frequencies, we tend to be negative. At the lower frequencies, it's going positive. We're getting more scattered here at the lower frequencies, meaning we're not getting a consistent site term. These values are similar at the high frequencies, but when we calculated our error, our epistemic uncertainty, I didn't use the range of these values. There's not enough data to say I'm going to get a standard deviation from 2 data points. Instead, we use the range from the full studies around the world that say how big our site response differences, divided by, in this case, 1 over root 2, the standard, and that's what collapses this down. So this is now our epistemic uncertainty range. If we take what this is about 0.8 from the high to the low, so half of that is about 0.4, so it's again, this is natural log units. That's the same kind of number you were just seeing in what Dan saw. So we do have large uncertainty, and we map that and we keep track of it. So you have to take uncertainty on head on. Yeah.
Could you just go back for a second? What exactly is 0 here? Is this a GMP? Is this a suite of GMPEs, or do you have a specific GMPE?
This was done for 4 GMPEs, so this is the average compared to doing the problem 4 times.
Okay.
So we did.
Ergodic.
Correct, ergodic. So if they fell along 0, they would have been consistent with an average site with that same VS30.
But it's a suite of 4.
Correct.
Not just one. Okay.
It's not just one, correct.
And how much does that change things? Because that's a question I'll raise. We've had others outside the IPRP raise the question of the validity of certain GMPEs.
Sure. So can you go back? So here is the residuals for one of the GMPEs, okay? If I repeat that for another GMPE, let's say it had the correct distance slope. Well, the example is the Cho and Young's model has a better distance slope than the other ones for this earthquake. Then the whole thing would have been centered, but by using the average residuals over the relevant distance range, I am taking out all of the fundamental errors, let's say, or differences in the GMP compared to that particular earthquake.
But that to me, again, looks like a tremendous scatter.
Absolutely.
So these other terms that are not in your, you've done a quasi, I forget what you call them, partially ergodic, partially non-ergodic.
Correct.
And it just seems like there's a whole bunch of other stuff that remains in the aleatory term.
Correct. It's big, and it doesn't go away. That's right. So when we do the partially non-ergodic model, our standard deviations go from, let's say, 0.7 down to about 0.63. Okay, they're still much larger than the 0.4 that I was showing you for the fully non-ergodic model. So that's why there's this big range that's left. This is, and when we go through the sensitivity, I'll get back to this. This big range controls hazard. This is the biggest thing that impacts our hazard at low probability levels. Okay. So the other, keep going down. So just to show you the orange lines on here are my error bars on my ergodic model. I would have said I expect it to be 0. It could be as high as here. It could be as low as there. Okay, so if I knew nothing, that's really what my range would have been. And I said, I still want a model site response. I'd say, I don't know if it's 0, I don't know if it's 0.4 or minus 0.4.
That's one standard deviation of that type of the table you showed, which broke those terms out.
Correct. This is plotted at 1.6 standard deviations, because that's what we use, the 5 to 95% level. Okay, so it's instead, one standard deviation is from the 16th to the 84th percentile. We broaden it out here to go from the 5 to the 95. But it's the same concept.
Yeah, is there one more copy of your handout someplace? I didn't get it.
Thanks, Laura. Appreciate it.
Good morning.
Yeah.
I noticed in your report, the new report, your fee S2S CAM, or that column is directly from the shoreline water report. But the shoreline water report was based on NG West 1, right? And then in this report is based on NG West 2. So it seems to me that you need to update your fee S2S.
So there's correct. So there's a couple of things. If you go back to the table down, so these tables of numbers, to get at these numbers, which table? Yeah. Okay. These are actually from Taiwan data. So a special study that had lots of data. So we had between 20 and 50 recordings per site for these kinds of data. And we see what these numbers are. So now there are other studies around that are, we're not just pulling those out of the NGA West data, we're also looking at it worldwide. There is, as part of the Swiss report, there'll be new updated numbers on what these are. So those will be out in the report that comes out in March, and we're propagating those uncertainties as well. So they are updated to be consistent with that, but they're broadened beyond just the data used in the NGA models. They're also looking at what the European data shows and what other this Taiwan data is all pulled together. Okay, but yes, you're right. This is from the 2011 paper, so those are not the same as what we get from the NGA models, but the numbers are very similar. They're going to be in this range of 0.35, something like that, 0.3 to 0.4. Okay. Next one. Yeah, so let's go forward. So I'm not going to go through this, but if you have the handout, this may help you. Okay, try to keep track of what we're doing. In a normal ergodic model, on the right, we take our ground motion model and we'll push it up to the top for an average site condition, like 760 meters per second. And then you'll go to your specific site condition for your 1D profile using a site response. That's, for example, what the NRC did in their RIL, okay, when they did their own analysis of this. So GMPEs pushed up to average rock site or reference rock condition, and then you adjust from that reference rock condition to your site-specific profile. Okay, so there's one adjustment that's done there using analytical modeling. That's how it's done. Okay, what we had done is we brought it up, our GMP up to the top, but then we also said, I'm going to compare now to my observations, and I see my site term is biased low, for example, at high frequencies, biased high at low frequencies with the uncertainty. So I'm going to bring it up, and I'm going to add to it that Diablo Canyon site term. That's now the term for where I have the free field recording. The free field recording is sitting on our two sites, but here ESTA 28 is on 750 meters per second. So I still need to adjust from the 750 to the site condition for the power block of the turbine building. So we do the same analytical modeling in that step as what the NRC would have done. That's the traditional site response step. So there are two parts to this. Ground motion model adjusted for the data, for the amplification, site-specific amplification at the free field station with its uncertainty, and then analytical modeling from that reference station to the power block or to the turbine building or to any other piece. And that's where, at this point in in the AB 1632 report, it was done with 1D modeling, and in our March submittal, it'll be done with 3D modeling of the site amplification. Okay, the next one. This is what that second step is, going from 750 to 1200 meters per second. It's very similar to what the NRC had used. The difference is we have a little more reduction because we have a deeper soil profile than what they did. So Z1 is the depth to 1 kilometer per second. So it's really sort of when we're going from the soils to think of it as a soil thickness. And so we had a little bit different there. But this is our differences here. So the main effect of going from 750 to 1200 from a soft rock to a hard rock is a reduction in the sort of higher frequency range there. Okay, next one. So if you put this all together, these are the deterministic spectra that you saw in the report. So the turbine building and for the power block, because they have different velocities, the turbine building ground motions are higher than the ones they are at the power block. That's from that second step of adjusting from 750 to 1200 or adjusting from 750 to the 980, I think it is. And this is, and you can see the shape now, our spectra, instead of a broad spectrum, which is what an ergodic model would produce, an average spectrum, we're going to have peaks and bumps and things like that in our spectrum that are reproducing the site amplification peaks that we see from those two earthquakes that we recorded. Okay? In addition, this is at the 84th percentile, so the uncertainty in that amplification is included in this standard deviation to create the 84th percentile ground motion. Okay, the next one. So moving forward, what we're doing right now, we're doing analytical modeling for the 3D site response effects. Okay, so we can see that there's quite a bit more complexity there using the 3 alternative models that Dan just talked about. And this is all going to be in our March 2015 report. That's the last one. Can you tell me? Oh, question. Last slide, and we had a question. Why aren't we using the ergodic model and bringing it along as an alternative? And so basically here, the data that even though we have this sparse data, it's not consistent with the ergodic model. So I have enough uncertainty that I don't need to build models that are inconsistent with the little data that I have. Same type of idea. Dan has 8 stations. He's got to be consistent with that. I need the models to be consistent with those given the range of uncertainty still that's in there. So if I looked at above the high frequencies above 5 hertz, the probability that these average site terms came from a mean zero, that is an ergodic model, is 2 to 3%. Okay? So I'm not going to build a centered model based on 2 to 3%. So I need to include it. So the data are really rejecting the mean zero model, but I have to capture the uncertainty. Right? So it's unlikely that they're centered there, but there's a broad uncertainty that I can bring along, and that's the way that we've addressed them. The next part, I think, is the hazard sensitivity. So do you have questions on this part, or you want to just charge forward?
Part of it that I think is you've gotten a little bit of this, and part of it I'm still struggling with is you have 2 earthquakes that show a consistent range of amplification for your recordings. You've shown that as an amplification factor, de-amplifying all the high frequencies. And, okay, that cannot come from a random ergodic model where you don't have something affecting those earthquakes affecting those recordings at that distance.
It has, let's say, only a couple % chance that it does. Right.
What we've talked about before, though, is what are the chances that you're mapping something else into that site term. This is a relatively small range of azimuths to those 2 sites. What are the chances that is a path effect or just something random? You have 2 flukes instead of, this is a lot of effect on the ground motion to be hanging on, but essentially it does 2 data points. Mm-hmm. And so seems to me that don't you have to consider the possibility that this is some other factor, or that these recordings are flukes in some way?
So by flukes, can you go back a couple, Dan, all the way to the site, keep going back.
Yeah.
That one, okay. So here's our range here. If we were to get it up to 0, again, these are the 5 and 95% ranges. So we would say there's a 5% chance here that it's a fluke, let's say. Over this whole range, it goes down to about a 2 to 3% chance that happened by these just two very unusual recordings, right? Right. The azimuths are actually pretty different between these.
Almost 90.
Yeah, so I wouldn't say it's the same azimuth. An issue is these are onshore, right? And is there different from an onshore path versus an offshore path?
There's a lot of structures kind of across the path of either one of these.
So what's going on here is really where I think we're seeing path effects coming through that are starting to be different. And if I look at, one of the reasons why San Simeon is way high here and this is, so I'm not getting consistency between these two, is we see those are some big surface waves coming in from that particular direction. So I think that's a case where that approach did not take out the path effects at the lower frequencies. And I think this is here more uncertain that we've got the right problem. But we're ending up close to an ergodic model there anyway. But here, the chance of getting these two with, as you said, almost a pretty broad difference. For us, 90 degrees is a pretty big difference in azimuth. That these things would be looking the same, I think, is unlikely, and that it's really controlled by a higher frequency site response.
If you looked at any kind of analytical modeling to see what could be filtering the ground motion along those paths, if there could be similarity along those paths, it would do that.
Yeah, so what you're talking about is let me go to the next piece, is where this all has to go to, okay, in terms of trying to get at that needs analytical 3D crustal modeling for that region to really start to get at that question.
I would just comment that peak at 2 hertz is simply a quarter wavelength over the velocity impedance from average near the surface to about 100 meters depth. It's just, you look at velocity profiles, you can go ahead and do the 1D, linear amplification, but that's where it comes from.
So Dan's had a little peak there at the lower frequencies as well, if you remember that, and that's similar to what's going on here.
And the difference at the high frequency, this site's generally higher velocity than his garden variety ground motion site.
These are, I wouldn't say that, these free field sites are in the 560 to 750 meters per second. So they're not really high. What we're getting at higher frequencies decaying like this is really being dominated by the kappa at the site. Okay, and kappa that's the damping due to, let's say, microfractures and things like that. In the top, we kind of wave our arms, but 500 to 1,000 meters is sort of where that gets accommodated. Damping in the shallow material, the first, tens of meters or 50 meters can't contribute enough to this. So this is really measuring what's happening sort of broadly in that area because you're propagating waves up through the Franciscan, and that stuff damps out some of the higher frequencies.
I think that's a very plausible explanation, but again, the frequencies of real concern are really between 1 hertz and 10 hertz, right? Bracketing those that really affect the threat to the plant. You see all kinds of uncertainty there, and I would submit, while your 90-degree azimuth difference between two earthquakes is not zero, but it's also, they are both onshore. I think that's hugely significant because you're talking about continental crust. One of them comes from or potentially, it comes at the San Andreas, near the San Andreas. The other, you're propagating through very different crustal sections than you face offshore, which is the direct nearest threat.
Remember that, so the reason why I don't just take the misfit between the prediction at my site And my recording, instead I correct it to take away the average from that earthquake propagating in the crust at those distance ranges.
But that goes back to that scatter diagram where you had, from those two recordings, you had amplification factors that were all over them, all in a huge range, where I guess one question is averaging that much scatter make sense? Does it really tell us something?
And the answer is yes.
Okay.
And
Okay.
the reason why.
Okay, go ahead.
Okay, so all that scatter is maintained in the standard deviation of the ground motion. And we'll get to that in the sensitivity. That I don't ignore that. What I'm trying to say is my global models give an average, so my GMPEs give an average for a global model, okay, an average site. I'm trying to say, does my site differ from the average global model? To get at that, I need to take away first the difference from the average global model and that particular earthquake in terms of how how energetic the earthquake was and how it attenuates with distance. So I have to have other recordings nearby or in that same distance range to be able to correct the GMPE. Otherwise, I couldn't do it.
Okay, so let me just for the IPRP, but before we move to the next phase of this, it seems to me there are just a couple of things for us to yet consider. There, you know, I'm working hard to try to keep up with this, but there seem to be two issues. One of them is, as you did the corrections from the free field site to the power block, all of those numbers went up. Those velocities went up, because you look on one of your slides here that has the velocity profiles and so you see the free field sites are both lower velocities significantly relative to the turbine building power plant. And the question of when we do that correction, that goes up, the higher velocity, resulting in less amplification. Why are we going up there? And the second question really then is related to the well, so I guess the question is, you look at the free field, you look at this plot that shows all sorts of different shear wave velocities here, and some of them, 11. It's 11. So you're seeing that in terms of characterizing the site widely construed, there's considerable variability from the boreholes, from the calculations that are done on the colored lines, and as was referenced in 6, in our IPRP report number 6, there's a question of, why do we use a high velocity? Why don't we use a low velocity?
So, I think maybe if I answer that differently for you, we would agree that these data tell you there is not one spectrum for the site.
Right.
In fact, we have to get a different one for every structure.
Right. And so how do we come up with VS30 under the power block at 1260 as opposed to applying the free field ESTA 27 as the VS30 under the power block?
Because it's not there.
Well, how maybe I missed it, but how have we calculated that VS30 at the power block is 1260?
So, Norm, I want to comment on one thing from the report here, and maybe help with Bruce. Figure 3-2 out of the CCC SIP report is essentially the same, except it shows everything in terms of depth, which is really hard to work with, and you fixed that. And one of the key things about this figure is it shows the power block at 0 depth and going down. And here you've corrected it, showing it's actually almost 50 feet below the ground, or it's about 35 feet below the ground surface. And so when you strip off that 30 feet of weathered rock and low velocity material, the velocity from there down is higher. And so
it's still high though.
What we've got here is two free field sites with one on each side of the plant. One at a relatively typical California hard rock at 570, and one at a significantly harder than typical, or faster than typical hard rock at 750. And that's in large part that free field site in 20A also has a lot of the superficial weathered rock removed. It's a free field site. And then if you go 30 feet below that into the basement and remove all the other weathered stuff, then you get some really high velocities. The comment here is, from what I'm used to, you're calculating ground motions, you calculate earthquake shaking at the Earth's surface. And so I look at the 570 and 750 and say those are a little higher than typical, but it's on a somewhat graded site, and so it seems reasonable. I actually was trying to draw in the old shear wave velocity profiles from the measurements back in the 70s, and they show this. The one there at SDA 28 has that high velocity bump in the shallow, which is also shown by the downhole measurement. They have a high velocity bump in the shallow, and that's there's a lot of variability, and but the V30s here from the ground surface down in the 600 to 700 range are fairly typical for just what you'd expect down here. And the one thing I don't know about this is when you have the ground motion, you calculate the ground surface with one shear wave velocity, and ground motion you can calculate at different elevations but different velocities. How do all those different ground motions feed into your structure? How do you do your soil structure interaction based on all of these different velocities in the whole area surrounding them?
So we'll use the footprint of one contained at a time, or one structure at a time, and we will use the average of the amplification over that footprint.
And the base of the, or do you?
Can you go to the foot?
Do you do the
go back?
ground motion of all from all of the material the plant is embedded into, right, or just the bottom?
So it's for the box that Dan was talking about. Yeah. So it is an expanded box. We put the ground motions into that, and then we can see what are the differences between what's happening here, what's happening here, what's happening in the turbine building, the ox building, whatever it is. They're going to be different. So what this data is really telling us now is is giving us the opportunity to refine our model to tell the differences between what's happening in different parts of the plant area. Where before we would just use one and we said it applies everywhere.
And so one end of the turbine building has much lower velocity than the other end of the turbine building. You feed both of those in?
Correct. So that's into the soil structure interaction has to deal with that input.
And so in terms of looking at the tables in chapter 13 where, amplifications and accelerations are listed here, I think that's one thing that we need to sort through and come up with our commentary.
A lot of those are for 980 or 1260.
Correct. And so chapter 13 is not 3D calculations.
Okay,
so those are simpler models.
And so, if you were to do 570 or 760 for the ground surface, you get different specs.
And so, is that something we would want to see, Chris? Is that something IPRP should look at, that range, a complete range of velocities?
I think for purposes of looking at the spectra from these earthquakes, we've already done that at 760, but not at 570. And so we can see the effect. It has a significant effect. If you want to calculate the shaking from these earthquakes at the ground surface using that velocity versus the foundation level using that velocity, and so it shifts everything and raises the.
And so that's that we can decide how that plays into our assessment of the uncertainty of the amplification factor based on some of those calculations.
Those are relatively easy things to factor in.
And the other point that I raised briefly was that, in talking to Sam Blakesley and other people that he's working with, I think we're going to get, the IPRP is going to get a submission that suggests that based on the choice of the GMPE, these numbers in these tables should be different. And again, I think that's something I think the IPRP needs to look at before we reach our.
It's relatively easy to do a sampling of GMPEs as well.
And so whatever commentary they have, I think, is something we need to look at and be able to respond to.
Sure. And then it's still, I think the factor that we need to be able to understand the basis of and understand that the uncertainty has been considered is that empirical amplification factor. I think that's still the big deal in the whole thing. And it still makes me awfully nervous that there's only 2 data points controlling that.
All right. Well, I just wanted to get that out to the IPRP.
That's coming back to the GMPs. I think that's something we definitely need to address.
Thank you.
So, when you review that, my one suggestion to you is pay attention to how they're using the GMPEs. If I take different GMPEs and compare them each to the suite of data recorded from Parkfield, if the GMPEs are different, one is systematically higher than the other, that gets, in this methodology, corrected out because I'm measuring my ground motion here relative to the average residual from those GMPEs. So when I run them, they're actually, those points that I showed you are very similar for regardless of which GMPE you're going to use.
I just think we have to go through the full calculation, or the full review of your methodology.
Right, you need to step, so what I'm warning you is don't jump to taking just the residual at the station and using that, because that's not what we're doing. If we do that, you would see inconsistencies. Because the earthquakes, one is more energetic at one frequency than another, and you would assume that's a site term when it's really a source term.
Well, but that goes back then to the question of just having 2 earthquakes to assess whether that's real or not.
Does PG&E intend to respond to the Blakesley testimony? Formally?
This cannot answer that.
So that the basis of this inquiry by Blakesley and others is he testified, and a colleague of his, Dan Hirsch from UC Santa Cruz, testified for the U.S. Senate Committee on Environment and Public Works. And in Blakesley's testimony, there's a technical appendix that's written, and it's, as I understand it, they expect to submit that technical appendix or something similar to it to us. And I happen to have a copy of it. I can forward it to the whole of the IPRP. But both Hirsch's and Blakesley's testimony are written and are the start. I don't know exactly what they're going to be asking of the IPRP, or what critique they're going to provide about the ground motion calculations. But I think it's important that we have looked at it and responded to it.
We also have in the state of California some very good expertise in ground motion. So Brian Cho at Caltrans is one of the best people around at this, so you might want to talk to him about that. Okay, next one. So hazard sensitivity. So because they're not hazard people really in this, I'm going to give you an overly simplified introduction to hazard just so that you know what we're talking about. So think about something really simple where I'm going to say, instead of a whole suite of earthquakes, I'm only going to make one earthquake, a magnitude 7, strike slip earthquake 10 kilometers away, and the geologists tell me that happens every 200 years. Okay? And I'm going to grab a single ground motion model, just in this next one. So if I do that, from my ground motion model, when I use that global GMPE, I'll get, in this case, an average, a median of 0.3 G, okay, from the ground motion. But there's a broad range, and this is what you were asking about. What about that huge variability? That's here. So when I know the magnitude and the distance, and I use my ergodic models, or my global models, you can see I've got here, this is about a factor of, from this point to that point, of 40 in the ground motion. It's huge. Okay, so this is from standard, or typical sort of standard deviations near, I think I use 0.65 in this particular case. To build a hazard curve, we're going to take this distribution as normal on a log scale. Okay, so it's a nice bell curve. I'm going to just sum it up from right to left. And that's what this is, just the cumulative distribution. So it starts at 0 and goes up to 1. Okay? So the 50% point, there's 50% chance, or the median is 0.3 G. Okay, the 84th percentile is where this would have been 0.16, is in this case about 0.55 G, for example. Okay? Now, my concern, the next thing is though, goes up to 1, but the earthquake only happens every 200 years. So the next one. So if I simply multiply that same curve by 1 over 200, that's what a hazard curve is. The chance of the ground motion being exceeded times the rate of the earthquake. It's nothing more than that. Okay, and we would sum them up for all of the different earthquakes and so forth going forward. Okay, because I care about what's happening down here at these really low probability levels, I want to be able to see something, I'm going to plot it on a log Y scale. So I'm going to blow this part up so you can see what's going on. So this whole part of the curve from here is now collapsed into this little tiny piece, but I'm going to blow up this part of the curve because we're worried about rare or low probabilities. Okay? What you see here is this curve, which is simply the shape of a normal distribution on a log scale, has a slope that's about 3. So it's steeper. It's not, this would be 1 to 1 on this scale, and it has a slope of about 3. Okay? That's important because the steeper the slope is going to affect what is going to control our hazard. Okay? So the next one. So we look at some differences. What happens if I took that blue line is where I started, that same curve, and what if the geologist came and told me that earthquakes don't happen every 200 years, they happen every 100 years. They doubled the slip rate of the fault. Okay, so I have more frequent earthquakes. All that I do is this blue line is scaled up by a factor of 2, which is this distance here, all the way up, and I go from the blue to the green. Because of the slope of the hazard curve, the effect of the source characterization has the biggest effect back here at these levels, and on this direction, not very much effect because the curve is steep. Okay, so changing the rate doesn't change my ground motion as much when I'm on the steep part of the hazard curve. If instead I went to a different GMPE and said, oh no, it's not an average of 0.3 G, it's an average of 0.6 G, so I doubled the ground motion, then I shift this curve factor of 2 to the right, and now you can see what happens here. So the difference between this direction and this direction is about a factor of 3, because this has a slope of 3. Okay, so instead of here going from 1 in 10,000 ground motions near 1 G, it's now near 2 G. If I looked at what's happening at 1 G, though the hazard level is going up by about a factor of 8. Okay, so the point of this is we're sensitive to what's happening on the ground motion characterization because we're on the steep part of the hazard curve. If we were looking at return periods of 475 years or something like that, more typical, then the source characterization becomes a dominant player in the uncertainties. The other side here shows you what happens to that aleatory standard deviation. So here I've run a big an aleatory value of 0.75, like an ergodic model on the high side. And here's what the hazard curve looks like. And then 0.4 is what you could get from a fully non-ergodic model. But that's as small as it went. And you can say, it's now a whole lot steeper. Okay, so that variability, that broad range that you saw in the scatter of the ground motion data is what's controlling this part of the hazard curve. Okay, so you can see this is down at these probability levels we're interested in. This is a huge factor for us in terms of what is our hazard. Okay, so now you can see if I was looking at just these two curves, I've got a factor of 30 or more in probability of what's going on. It's a much smaller factor in ground motion because the curves are steep. So when you're in steep curves, we can get the ground motion well constrained, but the probability is more uncertain than that. Okay? But I can't just do this and say, I'm going to use a non-ergodic model and use a smaller standard deviation. I have to have the penalty for not knowing those 3 terms, the amplification term, the path term, and the source term. Okay, so the next one. So this is the uncertainties. If I took 3 different models, if I said, yes, I'm going to say I'm following my site, source, and path all happen to be what is the global average, which is possible. Okay, then you would get this red curve. Here's my ergodic model. Okay, if instead I said no, those 3 terms summed up to say 0.4 higher, so that they were 40% more energetic, I would get this curve. I could have had another curve out here if they were out at 2 standard deviations or 4. And this is the lower one. So this is the epistemic uncertainty that has to be tracked when I do a non-ergodic model. Okay? The next one. So you can see this is a huge range of what's going on. If we look now at what are our uncertainties from the ground motion characterization side for a hazard at Diablo Canyon, so this is no longer just a toy problem, but it's running the Diablo Canyon hazard. These slopes here are still very similar to what we talked about, numbers at around 3. Okay, so even though we ran that the other example was overly simplified, the implications or the conclusions are still valid because we get those slopes for real cases. What's shown here, there's a bunch on this plot, is the range of hazard that I'm going to get if I chose different ground motion models. So this is what's coming out of the Swiss ground motion characterization. We've created a broad suite of what the ground motion models could be. We've taken the models from around the world and we said what is their range. Then it's the range from the blue curves. Okay, that's how much the different GMPEs can change the hazard calculation. So if I'm looking at 2G at 5 hertz, okay, that's kind of a number that we care about at Diablo Canyon. You can see what the range here is. So on the y-axis, it's a range of, say, about a factor of 40 in probability, but a much smaller factor if you're looking at it here on ground motion, it's about a factor of 2.5. Okay. Still bigger than the 40% we were talking about on this side. The site amplification, if I propagate the full width of what the site amplifications are, we get the range of the orange ones. And the green is if I use different values of what is the standard deviation, what is the aleatory variability term. That shows up mainly, as you saw earlier, at the lower probability, so that's tight and then broadening out. Okay? So the next one shows you what our tornado plot looks like. We've been focusing on the source characterization, so you've seen this part of the plot before. The blue ranges were what we were dealing with in 2011. The red points are what had come out of the improvements of the model from the particularly, for example, slip rate on the Hosgri in terms of reducing uncertainty. But what you see on top of that is the range that we are working with of the cost of taking global models and assuming they apply to my site-specific application. Okay? So that cost is broad uncertainty. And so you can see the value of what is the sigma, standard single station sigma model, what's the range of the site amplification, and what's the range of the medians from the GMPEs. So there, and probability, right? So this is a ratio of the y-axis, not the ground motions are larger, but you can see we're looking at factors of 10 to 20 or more. Okay? So these become really dominant, and it's hard to, so improvements down in the source characterization, while we can still do better, are going to be looking through the blurred glasses of the ground motion world that you really can't do much better to refine our total uncertainty.
What is the time-dependent hazard?
The time-dependent hazard is just looking at saying, we calculated earthquake rates or long-term slip rates, but is there a periodic, is it going accelerating and changing over time instead of a Poisson recurrence rate? Okay. The top two on there are sort of similar to what we're talking about for the site and the median GMPE, but what if we could pull out the path term? Okay. So right now, if I say, I believe there is a path term, I just don't know it. Okay, so now we've run the hazard analysis for a whole suite of different alternative values of what that path term could be, sampling the full range with, in this case, total ignorance. So we have a broad uncertainty range. Then you can see what's there at the top, which is our biggest uncertainty range. So now this is our largest piece. And to move forward, if you really want to reduce uncertainty and hazard, you have to take on that piece. We can't do better with the medians from the global models because those are always going to be differences in what is from a global average to my site. Okay, and I'm never going to get there until I start to get the site-specific and path-specific data to be able to take on those top branches of the model. The next one. So we've been talking to the seismology and earthquake hazard community about this. So how do you reduce uncertainties in hazard? So for low probabilities used in nuclear power plants, we're on the steep part of the hazard curve. So this conclusion doesn't apply to all hazard calculations. It's really to critical facilities where you're pushing yourself to low probabilities. So for steep hazard curves here, the hazard uncertainty is much more sensitive to the ground motion model than to the source characterization because that slope is about 3. Okay, so there's sort of 3 times the leverage of a change in the ground motion model compared to a change in the source model. So the key improvements are really going to come by site and source specific ground motion models, not another round of updating the worldwide models. We'll keep doing that. That's still be done over up here, and they'll have another range, but that's really not going to get at our fundamental issue here, and that is we're taking a model for an average site condition and earthquake condition around the world and saying our site is that. So the way you can get at this is site-specific ground motion models for path terms, and then or site-specific ground motion models. I shouldn't have put that. This is just the site terms, and then the path-specific has both the site and the path terms. So can you correct and just write site terms in there instead of path terms? So the next one, I think some of you were at the SCEC annual meeting last year where I talked about this problem and how to move forward. So how do we constrain path effects? What are our options? So you can mainly use small earthquakes because that's the way you can get a lot of data. The path terms are linear, right? So we're not worried about non-linear behavior. So the little earthquakes and even microtremor can be used to start to help you on this. Currently, though, we still don't have dense enough coverage to get out to some of the issues that we've just discussed. To fill in, you can do numerical simulations with the 3D crustal model, so you can do that for dense coverage if your model is accurate enough to give you that density. So then you have a whole issue of the validation and calibration of your 3D model. I won't talk to you about this, but we did look at, do we get similar results between data and observations looking at data in Southern California from CyberShape versus the NGA West 2 models that have overlapping regions, and we can compare path effects. The answer was the site effects they were getting were good. The path effects, some were improvements, and in some areas of the model they were actually not working very well. That is, we have to have empirical calibration of this. You can't just say that here's a 3D crustal model, believe my results, and move forward.
We were having trouble getting the 3D crustal models simulations to work for any kind of high frequencies.
Correct. That's being addressed now. So
it was kind of getting sort of calibrated at like 3 seconds and longer or something like that.
Correct. And that's what this check was done, but they can now run them to 5 hertz. Okay. So that's been a big.
They're working on getting it to somewhere that's relevant to the problem here.
Correct. And so the next one is for path of terms. If we're going to get to 3D simulations, we need an applicable 3D velocity structure in the Central Coast region that there hasn't been a good model developed. But it also requires validation not of the arrival times, but of the amplification. That's what we care about, is amplification. So that has to have some ground motion data to be able to test parts of the model. Okay? Empirical data, again, will be limited to small earthquakes for path effects because that's the only way we're going to get enough recordings to get at it. And then there's an issue about how we extrapolate path effects to larger magnitudes because a big earthquake isn't a point anymore. It's rupturing over a volume. We think we can use the simulations to help us get at understanding that behavior. We did look at some of that for the CyberShape runs and found for the big earth ruptures, the path effect from the closest point of the rupture was similar to the path effect for the whole thing, but that still needs quite a bit of checking. Next one. So, does it make sense? So, are we ready to take this problem on? This is really what I had presented at SCEC, and then there's been a workshop at SCEC in August and one at the USGS in November where essentially we're asking them this question, can you do this? Do we have the data to work to take this problem on? And so the conclusions are really there is adequate data currently to start to build a model. SCEC is in particular using microtremor and data to build 3D crustal models as a first cut at the velocity structure, but also then using the available data to build a 3D model. The 3D simulations now are fast enough to allow rapid feedback. And this is really a key, that they can turn these around in about a month so that you can see the results, compare them to your data and observation, change the model and have feedback and rerun it. If this took 2 years to run, you can't get that. So that's really a huge step forward just in the calculation speed that's available. And I didn't put this down here, but we're able to run now, again, numbers of 5 hertz are feasible at this point. Really though, we're gonna need additional seismic stations to start to get enough data to really start to constrain what's going on. We're severely spatially aliased right now. You know, we have samples and they're 10 kilometers apart. What's happening in between those 10 kilometers is an issue. We're looking at traditional seismic stations, but I think there's got to be a new concept of inexpensive alternatives to how do you get out 10,000 or 100,000 instruments and they can't be the kind of scientists normally want to work with. It's got to be a different thing. Similar to how the oil industry puts out huge sets of sensors when they do their surveys. I think there's solutions to this, but it needs a different approach. The other part is checking this whole approach to going to areas where there's good coverage right now. One suggestion is the Anza area in Southern California where there's a whole lot of data and earthquakes, and can you see how much improvement is possible with this method? Again, and testing of path terms, I think they'll need some new metrics to really quantify how good they're getting at that. And really this is a multi-year application stage. So we're talking about, thinking about this in our future, moving towards, let's say, a 2025 10-year update of the hazard for Diablo Canyon. And I think that's it. I'm almost on time.
One of my questions was, how much is this going to get done by March?
None. So this is part of the, so what I've been getting from the SCEC and the USGS is really feasibility and how do you get started on this whole thing. But to make big improvements in our understanding of the hazard, we have to take on the path effects. I think anything else, we're just kind of fooling ourselves.
In terms of what we have to look at in the current evaluation of the hazard plan, the top of the tornado that you have a value that you're proposing on is that the site amplification in the sigma SS model. The things above that are data intensive that you're not going to. So they're not telling us anything new about.
That's right. So what you'll see in March, we'll have. Can you go back to the tornado plot? So it will have the green ones in it. Okay, and so that comes out of the Swiss model.
Okay, that's green.
So we will, and I should say, the 2 top ones are not going to be there. Okay, because that's really a new approach that no one is using at this time. Okay, but
no one is using because
they don't have the data.
Don't even have 2 data points to hang anything on.
Correct. So there is a workshop in the Europeans are starting to look at this. So this is coming back to Bayesian updating of seismic hazard. So if you think of your global model as your soothed model, and then you start to use the path effects to update that model in a Bayesian way. So that's one framework that this really works well in. So that's going to be discussed in February, so next month, in terms of the feasibility of this approach. Okay?
The highest topography in the models, the less than 200 meters above sea level.
And is that going to be the depth for if you do numerical set response, 3D set response?
Yeah, so we need to input the motion at the base of the profile for the amplification. But the model is used to get the relative ground motion at different locations. Okay, so we want to be able to say what is it at unit 1 compared to unit 2 compared to north end of the turbine building or south end of the turbine building or whatever it's going to be. So that's really what it is. It's a scaling back and forth. It doesn't tell you the absolute level of the ground motion, only the relative amplification.
Okay, so it seems to me that probably reflects what more of what a VS30 would do.
Correct. Yeah.
Rather than the site term. So is there any way that we could gain more confidence in terms of the site amplification term?
Yeah, so you'll be able to compare the VS30 effects. So one way will be compare what's in GMPEs for simple VS30 scaling versus what comes out of the 3D amplification scale, and it will be different. And in some places it could be higher, in some places it could be lower. It won't be systematically one way or the other.
But the empirical site term, the de-amplification term, is before you go into the 3D model or afterwards or
It's
mixed?
separate. So the 3D model for us is doing the step of how do you move ground motion from the free field sites to the different structures.
Right. But the input to that is?
It's the same, so we wouldn't change that part of it. So that will be, what you're reviewing now will be the same part of what's in the March report.
So I think that, so the site amplification term, the empirical term, is a larger scale feature than your
Correct.
model.
Correct. Right. So that, because it's empirical, it samples deeper, right?
Whatever it is.
Yeah, whatever it is, yeah.
Going beyond the 1632 study, do you have any plans to do this similar analysis for the ISSC?
No. So I can tell you we don't have plans. We haven't talked about doing that for the ISPC. The information is there, right? So your 3D, does your 3D model go all the way up there? No?
Yeah, it's right up now.
It's up in the corner,
Yeah.
right? Yeah. So those numbers will come out of the calculation, but for March, we're focusing on the power block stuff. But they'll be there, because when you run the 3D, you get it everywhere, right? We just have to pull the results out at that point.
But we use the modified Oscar 77 Oscar spectrum. This was the assessment. We use the modified 77 Oscar spectrum
But
for
for
the
ISPC,
assessment.
when we did the design spectrum, we took Oscar, we broadened it into its higher ground motions already, because we wanted to make sure we wouldn't have to retrofit it later on. So it has extra margin in it, but I think the question is, if we give you 3D effects at the power block area, what about at the ISPC area? And those number calculations are being done, but that's not part of our March submittal, but we'll have those available. I'll make sure we pull them out and save them. I think that's the key thing.
And so the March submittal is the whole output of the SHAC process to NRC, and that's going to be public and available to us at the same time, or is that?
I think so.
So I think that's one of the things I think one of our next steps, maybe it's 2 steps down the road,
You get it
is
maybe
that
later, but yes.
we being able to look at how all of these different factors go into the analysis there, I think is something we certainly want to look at. Be able to review the way we've reviewed
do the source
steps along the
characterization
way.
report, the ground motion characterization report, the site response calculation, and then putting it all together into the Haskell.
Might take, is that another 1,800 pages of
That's
text?
yeah.
Bill rival.
But I think in question of future work for the IPRP, I mean, hearing about the site amplification based on the 3D modeling, I think that's something we should reasonably look at, because that's an extension of what's in this report. I look at it as a refinement. You're going to come up with these same tables based on a different modeling system. So I would think we have reason to convene again on that and a number of other issues to look at that.
I think just from our perspective going forward, we've done a third of the meetings on the CCC SIP report. I think this one was the third because there was going to be additional work on that and additional time to incorporate our comments into your analyses. And the source characterization was very short term. You needed our input quickly. So like we did on the last 2 meetings, that we'll try to have a report out within 30 days saying what our conclusions are from what we've seen. And
I wonder, Chris, whether we're ready to even draft a report based on the question of the GMPE issues that Blaise and others are going to raise. I mean, my preference would be to set another meeting and get more input.
We may need to talk to them, get their perspective in a working meeting.
Yeah.
I don't think we'll probably be able to schedule a public meeting to talk for the week. We might be able to do that within a couple of weeks and then move forward. And might mean our typical 30 days isn't an achievable target.
I think it's important, particularly because the tornado is gotten wider here.
Well,
right?
No, I think this is something that we did this a little, not quite so elegantly. In IPRP report number 6, we said that the ground motion is the top of the tornado. Ground motion characterization is the top of the tornado. These are the important factors we need to make sure we understand where the uncertainty is coming from, and that we can look at how you can reduce the uncertainty in seismic hazard, which is our charge. So, and advise on that. So that's.
But I guess I would argue that I'm not prepared to say what I can about the IPRP's conclusion on chapters 10 and 13 until we get some more information.
We want to get their perspective, and just one of the things that we focused on previously is how well do you understand the velocity structure underneath the plant? What is the V30? What is the variability in velocity with in all 3 dimensions across that? And what we had before was 3.5 velocity profiles from the 70s, and V30 that it was kind of borrowed from this, and that characterization of what's underneath the plant from the tomography is much more detailed. There's a lot of actual geology structure that appears in there, and to the extent that you can check back against the really crappy old data, it's consistent.
But don't you think there's a question we need further discussion on as to how we translate those velocity measurements at the free field site into VS30s for other places on the...
Well, and I think that's one of the things we can do. It's very easy to do, is say the velocity at this side of the turbine building is this value. The velocity of V30 at this side of the turbine building is one number. The velocity at the other side of the turbine building is another number. And it's very easy to do that. Throw the V30 into the calculation, calculate a deterministic spectrum, and say how does this compare?
Which is what they're doing with the 3D. So I would like to see the 3D models to see if that kind of analysis, which the 3D models are an extended version of, right, makes sense. The other thing is to talk about the consequences of the 3D tomography. There's an extensive discussion of the limitations of the 3D tomography in the uppermost part of the section because of the crossover points and the lack of first arrivals. And I'm not completely clear. And again, if we might meet again, maybe we could get a little more clarity on what that does in terms of constraining or not constraining uncertainty and velocity structure in that very shallowest part of the section.
I saw that, Dan, you might want to comment on how well constrained is that shallowest velocity directly underneath the foundation, because that seemed like that was the toughest part to get raised through.
Yeah, that was something that was best constrained by the measurements directly at sites, of dispersion or from the downhole, because the travel times to the shallow part, place a very strong constraint on the average velocity over the top 5 meters, and that was where I was having the trouble, very top of weathering, because of the limited offsets. And so I didn't put them in about a half plots showing where the rays start to really pick up, So that's why, in the review comments, they said, you really should be looking at all the data you have. So that's why I put those 9 data constraints in, because they provide strong constraints where the refraction had the trouble, which is the first 5 to 10 meter.
But it seems to me that,
The constraints are from the 70s era.
Yeah.
Did you go back to the 1960s Bloom surveys? Or?
Yeah, those are really shallow.
Yeah,
but those are all in where they've now replaced that material.
Oh, it's all in the graded area that was gone.
Yeah, that was, those 4 were focused really around Unit 1. And
so they measured the velocity of the material they then removed.
destroyed the evidence, yeah. But
not terribly helpful.
But it's the meshing of all those different sources of data that goes into the 3D models, right? And so I'd like to see that, because you've got limitations on spatial sampling from the boreholes, and we're talking about things that vary spatially. You've got averaging issues when you do surface wave dispersion, because you have to measure that over a certain volume that's, so I mean, I would like to see how that was all brought together in the 3D model. So again, topics for further consideration. If we're to do, again, I go back to the thought that what we're seeing is that the greatest uncertainty is in this particular segment of the work. I think it's important for us to be careful in being thorough.
It's clearly
right.
The factor we need to understand the best.
So what time it takes us to do that, I think is well spent.
I think other members of the IPRP want to weigh in. It sounds like you're suggesting we do a working meeting with Dan to just go through the details of how you can constrain the shallow velocities.
That's one topic, and a working meeting with Blakesley or whoever he wants to bring forward.
See what their issues are.
What their issues are.
Those could be good to do.
Yeah. And then see whether there's another public meeting that's appropriate or necessary. And then I had just 2 things while we get them out on the floor. One of them is, I've been asked by a number of people from very different quarters whether the IPRP would put forward a summary report. They have our serialized version, like the great novels, right, appeared in the New Yorker or whatever it was, Harper's Bazaar. But whether we would do a summary report of our, once we concluded, and whether that summary report might be presented in San Luis Obispo County. We can certainly make time before our Board of Supervisors or within a different setting to, I think it would be very appropriate and very much appreciated by the residents of the county to have the IPRP, or as many of the IPRP as can, come and present in person.
So I think we have these comments, and Eric, you might want to weigh in what the PUC's view of this is. In a sense, we're giving advice to PUC. We can sum up our comments on the CCC SIP report, which is what we've been working our way through over the last few months. Or we could, in 6 months or so, do a report in which we summarize that and what is presented to NRC. And that would be quite a different IPRP report. And I suspect either one of those could be presented to San Luis Obispo County residents, concerned citizens, and so on, and would be appreciated but it seems to me that kind of at the end of the process means more after the fact reports go through and we can get a chance to look at it. Eric, do you think that's good?
Those are several very good options. I was originally only thinking of if there was an opportunity for PG&E to add either an appendix or a supplement to their SIP, a very slender volume, which would just contain our reports, let's say, and PG&E's responses, so that it wouldn't be creating any new text, but just to have in one place somewhere, a repository for all of our reports and PG&E's responses. But Bruce's suggesting that, all of our reports or, discussions and, could be let's say, summarized in an additional, summary report, which could also then somehow get folded into, the SIP, and that could be presented at, let's say at some public workshop in San Luis Obispo. I mean, that is a very good idea, but, we can just continue to, explore that, offline. I mean, it's certainly reasonable to do that.
And probably just in terms of talking about public presentations, we've all discussed this within the IPRP, but Stu and Janet Watt at USGS and one other, I forgot. Neil Driscoll at Scripps have organized a session on Central Coastal California tectonics at the Seismological Society of America meeting in Pasadena in April. And for some reason have asked for a perspective from the IPRP on the studies of the tectonics of the Central Coast and what we've reviewed. And so I put it in an abstract, which you've all seen, describing what the IPRP is, and does, and has found so far. And that's, in case anybody actually cares to show up at that public workshop, there will be a 15-minute presentation on that.
What's the date?
I believe it's April 22 to 24, something like that. So that's a public discussion of a number of science findings from various reports, some of which are related to these CCSIP and others that are others by USGS and other scientists working in the area, and then a little bit of perspective from me, and I'm try to represent all of your opinions on the panel of what we've seen so far and our general conclusions.
Do you intend to go into the ground motion part of this, or just because my impression was that the session was mostly about tectonics?
It's mostly about the tectonics. I say I do a one-sentence summary of each of our last 3 reports, saying the uncertainty in seismic hazards due to the Hosbury and Sansemian slip rates has been reduced by the CCC-SIP studies, whereas the uncertainty in seismic hazards due to the faults in the Irish Hills has not been significantly reduced. And the IPRP is anticipating releasing a report on ground motion issues sometime early 2015. So that's not done yet, so I didn't say anything, except that we're working on it.
No, I remember that, and in the abstract, I was just meaning when you're at the session, which is
we will have
2015.
we will have to see if we have any actual conclusions to present.
A month after.
April's a long time away.
April is a long time away in terms of our typical 30-day turnaround, so we hope to have something, a couple of meetings before then.
Has this kind of plot ever been shown at SSA? I mean, I think that's a great...
The tornado diagram has gotten to be fairly common anymore.
So that was displayed at the SCEC meeting in September.
So people have seen the lower half.
Yeah, adding the upper half is kind of mind-blowing.
Well, and I think it's a really useful construct. I mean, and again, in that interface to public policy, uncertainty is really where it's at.
Well, the other part that's interesting is in terms of how public policy and seismic hazards get our interface, is that the tornado diagram is a construct from probabilistic seismic hazard analysis. And you're looking at the sensitivity of that type of hazard analysis to all of these factors. And there are still the people, and there's another session at SSA of people who feel that the deterministic analysis is still the appropriate type of analysis for critical facilities. And so that type of analysis doesn't really allow you to compare uncertainties. because it's a scenario-based analysis. And so you don't necessarily know or care about the probability of any particular event or the uncertainty in that. And so presenting this in terms of a tornado diagram, almost it shows that you're thinking of these things in the probabilistic framework. What is the likelihood of any of these events? What is the uncertainty in that likelihood?
Right.
So that's something that, even if you go there and presenting a tornado, then you are showing that you are using a type of analysis that not everybody agrees with.
I have lots of interesting conversations with members of the general public and even technically minded folks who struggle with this.
It's very difficult to get members of the general public and even members of SSA sometimes to realize that a deterministic analysis is not a worst-case scenario.
Yeah.
And there's never been a worst-case scenario used in any public policy. And so that's one of the key things that if you're doing something that has a likelihood, then you have to do probabilistic to understand how it compares to other things.
But then you have to make the choice of what you're willing to accept.
Right.
And that's
it's
more argument. That's more discussion.
It's a tough thing to do with non-specialists and people who don't do seismic hazards in part of their regular work. So anyway, that's something thinking about your public workshop is something that has to come out in it. How you think about a tornado diagram.
Right. I mean, what conclusions you're going to draw from this work, which is really, in the end, what we have to do.
The whole point of the whole AB 1632 studies is find out more about the structures and seismic sources in the area, how you do these ground motion calculations, so that you can reduce the uncertainty in seismic hazard. And so we've been brought together to advise and review, have any of these studies actually reduced the uncertainty in seismic hazard? And so try to say something about that in public. It's always a challenge how to frame that.
Fascinating stuff.
Okay, so next steps are possibly a couple of working meetings with both to understand the 3D model a little better, and then other folks who have other issues about the ground motion equations. An IPRP report in 30 days plus a few. And then don't know if we have another public meeting before March. Certainly when we have the shack submittal, I think we need to start to think about scheduling, seeing what kind of volume we have there to review, and then think about a public meeting after that.
And the only asterisk I wonder if we could put on that is IPRP report pending the outcome of those working meetings and whether more needs to be done before we're ready to issue that.
Yeah, that makes sense. Other comments, questions?
I have two comments. One is timeline for completion of activities through March 15th. The first one is if in fact the IPRP were given some room in the PG&E documentation or companion document for PG&E for the NRC, then we'd have to have a backwards time horizon to have everything done that we want to have in this appendix and have it set so it's reviewed, done, given to PG&E to submit with their timeline for sending stuff to the NRC. So there's some problems with that, especially with the 3D review for Chapter 13. So we'd have to have it early enough to know what is going on. The other thing to look at is having some kind of interim report outside the SSA presentations.
Yeah,
I think is premature, and would recommend getting out whatever goes to the NRC in March and whatever we have concluded by then, and then presented it at the county or elsewhere here in San Francisco in the spring or early summer. quickly after March 15th, but not before. So it's, yeah, I like it. I think it's reasonable, but I think March 15th is too early. It's not determined. And then have a chance to make sure it's good enough and simple enough for people to understand.
Right, in terms of the public, in
Yeah,
terms
yeah.
of the general public,
Yeah.
absolutely.
Yeah.
That's going to be, that's a really important function of this panel, and one that I think you're going to have to put some thought into.
So, one thing that reminded me of, is we've talked a couple times about our reports and then PG&E's replies to those. Have we received a reply to either of the last two reports?
No, we're going to wait for the next report to be issued, and then I think because all of these are related to the CCCSIP, we'll just file one response to all three of those reports at the same time. Now, I would note that for the earlier reports, 1 through 6, and our responses, I believe we have submitted those all publicly to the California Energy Commission previously in the IPR, and those are all part of the public record there. In a data request response we provided about a year and a half ago.
I believe the responses are they on the PUC webpage?
Yes.
Okay,
Yes,
Eric
they're on
would
the
know
website
that
as well.
yeah. So those are out there publicly.
It seems to me that, this is, that the last two IPRP reports are kind of as our comments on the seismic source characterization parts of the CCNCS IP. And if you wanted to separate those from the current one we're going to be working on the ground motion aspects, that would be two very, very different replies. If you separate those two out, that would be, it might be easier to do rather than bundle those together.
We'll take that back and think about it.
Think about that.
Yeah, but
Think about
right
that.
now, I mean, because it is, one body of work and all of that is included there, that having one summary response on those report issues.
We pushed pretty hard to get those two IPRP reports out to you in time for you to consider them in the ground motion, in the seismic source characterization as got built. So we hope they got noticed and used.
Considered.
Considered.
Thank you.
Okay. Other comments? Are we done? We're not scheduling anything in particular, and we don't have a next meeting on an agenda on the schedule, but I think we've talked about a number of things that are going to be coming up in the near future, and then off in March, getting another large set of reports that we will try to figure out how to review.
I'd just like to thank everyone for coming and taking the time to participate and, contribute. It's very useful for all of us. Thank you all for coming, and we'll keep everyone, posted about, future activities. Thank you.
Thank you.
Stu, Norm, or you have these as PowerPoint files that you can forward to us?
Yeah, we'll
It would be nice to have the PowerPoint files of these. Because then you'll see that tornado in the report back to you.
The new tornado.